All right, welcome. Today we are going deep, and I mean really deep, into one of the most important and honestly most elegant tricks in all of electronics, pulse width modulation, or PWM. Now I know, that sounds super technical, but trust me, this is the hidden magic that's running your world right now. It's how your phone screen dims, it's how a drone hangs perfectly still in the air, and it's how an electric car delivers power so smoothly and efficiently. Our mission today is simple. We're going to build a complete understanding from scratch. We'll start at square one, assuming you know nothing, and by the end of this, you'll get not just the what and how, but the really clever engineering that makes it all possible.
Okay, so here's our game plan. We're going to build this up step by step so it all makes sense. First, we'll talk about the why, the big power problem that engineers had to solve, which made PWM a necessity. Then, we'll pull back the curtain on the simple but brilliant on-off secret at the very heart of PWM. Once we get the concept, we'll dig into how these signals are actually made, both the old-school way and inside the chips we use today. From there, we'll look at some of the pro-level variations, the different flavors of PWM. Then we'll connect it all back to your daily life, and you'll start seeing PWM everywhere. And finally, we'll get into the main trade-off, the electronic noise, or harmonics, and how engineers have gotten really good at taming it. Let's get started.
So let's start at the very beginning, with a problem you've definitely experienced. Picture this. You've got a super bright LED. It's on at 100% full blast, and you want to dim it down to, I don't know, half brightness. How do you do it? Well, the first thing that probably jumps into your head is just give it less power, right? Lower the voltage. And yeah, you can do that. But that simple, obvious solution has a huge hidden problem. You end up wasting a ton of energy.
Really, there are two ways to think about this. On the left, we've got the old way, analog control. Imagine we stick a variable resistor, like a classic dimmer knob on a wall, between our power source and our light. As you turn that knob, the resistance goes up. This kind of strangles the flow of electricity, the voltage to the light drops, and it gets dimmer. Simple. But here's the billion-dollar question. Where did all that blocked energy go? It didn't just vanish, it got turned into heat. The resistor itself literally gets hot. It's like trying to slow down a fire hose by stuffing a sponge in it. Sure, less water comes out, but the sponge gets blasted with all that force. It's just wildly inefficient. Now look at the right. Digital switching. This is the smart way. Instead of a resistor that gets hot, we have a perfect switch. A modern transistor is basically a perfect switch. It has two states. It's either completely on, acting like a perfect wire with zero resistance, or it's completely off, like the wire's been cut. And in both of those states, fully on or fully off, it wastes practically zero energy as heat. This is the whole key. But it creates a puzzle, right? How on earth can you get a dim light if your only options are 100% on or 100% off?
And this, my friends, is where the absolute genius of pulse width modulation comes into play. It's the answer to that puzzle. It lets us have the best of both worlds. We get that smooth, fine-grained control of an analog system, but with the amazing energy efficiency of a digital switch. And the secret has nothing to do with changing voltage. It's all about being clever with time.
So, let's nail down a definition. The name tells you everything you need to know, just break it down. Pulse width modulation. We're generating a pulse, right? A square wave that goes on and off. We are modulating it, which is just a fancy way of saying we're changing or controlling it. And what part are we changing? The width of that pulse. That's it. So we're controlling the average amount of power something gets by changing how long the on time is compared to the off time. And here's the crucial bit. The voltage level, the height of the pulse, never, ever changes. When it's on, it's at 100%. We're not touching the voltage, we're playing with time.
The best way to get this in your head is the water tap analogy. It's perfect. Imagine you need to fill a bucket halfway. The old analog way would be to just turn the tap on a little bit, letting the water trickle out. It works, sure, but the valve might be hissing, it's just not very precise. Now, the PWM way is totally different. You would turn that tap full blast for exactly 1 second. Then you turn it completely off for 1 second. Then full blast for a second, completely off for a second. On, off, on, off. You see? Even though the water is only ever coming out at full pressure, because it's only on for half the time, the bucket is going to fill up at half the speed. You're controlling the average flow by controlling the ratio of on time to off time. That is exactly what PWM is doing with electrons.
Okay, now we need to learn the most important piece of jargon in the world of PWM. It's called duty cycle. It sounds a little intimidating, but it's dead simple. The duty cycle is just the percentage of time the signal is on during one full cycle. That's it. In our water tap example, one full cycle was 2 seconds long, right? 1 second on, 1 second off. The tap was on for 50% of that time. So that was a 50% duty cycle.
If we wanted to fill the bucket even slower, we could turn the tap on for just 1/4 of a second, and then off for 3/4 of a second. That's a 25% duty cycle. This percentage is our new digital knob for controlling power. 90% duty cycle, high power. 10% duty cycle, low power. It's that simple.
This table right here makes it all crystal clear. Let's just walk through it. Say our power source is a steady 5 volts. If we set a 0% duty cycle, well, the signal's always off. Average voltage is 0, the LED is off. Duh. Now, let's try a 25% duty cycle. The power's on for 1/4 of the time and off for 3/4. The average voltage that the LED feels is 25% of 5 volts, or 1.25 volts. It'll light up, but it'll be dim. Move to 50% duty cycle. On half the time, off half the time. The average voltage is 2.5 volts. Now we're at medium brightness. Do you see the pattern? At 75%, it's on for most of the time, giving an average of 3.75 volts, and it's pretty bright. And finally, 100% duty cycle just means the switch is always on. The LED gets the full 5 volts and is at its max brightness. Now, you're probably thinking, wait a minute, wouldn't I just see a flickering light? And that is a fantastic question. The key is that this on-off switching happens incredibly fast. We're talking hundreds, thousands, or even millions of times every single second. It's so fast that our eyes, or a motor, or any other component can't possibly see the individual pulses. All they respond to is the average effect. It's like we're tricking the LED into thinking it's getting a lower, steady voltage, but we're doing it with zero wasted heat.
Okay, let's take a quick breath. So we know what PWM is. It's controlling power with on-off timing, and we know why we use it. It's super efficient. So the next logical question has to be, how? How do we actually make one of these precise, high-speed square waves? We're going to look at 2 main ways, the classic analog circuit way and the modern digital way you'll find inside something like an Arduino.
First up, the classic analog method. At its heart is a really cool little chip called a comparator. All a comparator does is look at 2 voltages and tell you which one is bigger. That's its whole job. So here's the trick. In step 1, we create a nice, steady DC voltage. Let's call this our reference voltage. Think of this as the signal from our dimmer knob. Higher voltage means we want more power. Then in step 2, we generate a completely different signal, a triangle wave that's just going up and down at a constant speed. This is our carrier wave. Now for the fun part. In step 3, we feed both signals, our flat reference line and our moving triangle wave, into the comparator. The comparator is now constantly asking itself one simple question. Is the triangle wave's voltage lower than the reference voltage right now? As long as the answer is yes, the comparator spits out a high signal. But the very instant that triangle wave climbs above our flat reference line, the answer becomes no, and the output immediately flips to low. Do you see what's happening? It's like we're using our reference voltage to slice the triangle wave. If we raise our reference voltage, we slice the triangle higher up, which means the output stays high for a longer slice of time, a bigger duty cycle. If we lower the reference, we slice it closer to the bottom, creating a narrower pulse, a smaller duty cycle. It's just a really clever way to turn a voltage level into a time duration.
Now let's look at how this is done today, inside pretty much every digital chip. It's a purely digital process, but it's basically doing the exact same thing. First, inside the chip there's a special bit of hardware called a timer. Its only job is to count, really fast. It starts at 0, counts 1, 2, 3, all the way up to some max value, let's say 255. As soon as it hits 255, it instantly resets to 0 and starts all over again. If you plotted that count over time, you'd get a perfect digital sawtooth wave. It's our digital version of the triangle wave. Next, you, the programmer, decide on a duty cycle. Say you want 50%. You'd write the number 128 into a special little bit of memory called the compare register. This is our digital reference level. Now the chip's hardware takes over. It's constantly comparing 2 numbers, the current count of the timer and the number you stored in the compare register. The logic is simple. As long as the timer's count is less than your compare value, the output pin is high. So it's high for counts 0, 1, 2, all the way to 127. The moment the timer hits 128, the logic flips the output pin to low, and it stays low for the rest of the count, all the way up to 255. Then the timer resets, and the whole thing starts over, thousands of times a second. It's brilliant because it's so precise and requires almost no work from the main processor.
And if you've ever played around with an Arduino, this will be a huge aha moment. There's a command called analog write. Now that name is a little bit of a lie because it's not making a true analog voltage at all. It's generating a PWM signal using that exact digital method we just talked about. When you type analog write pin, value, all you're doing is telling the Arduino two things: which pin you want to use, and what number from 0 to 255 you want load into that compare register. It's that simple. If you write analog write 9, 0, you get a 0% duty cycle. The pin is always off. If you write analog write 9, 128, you get pretty much exactly a 50% duty cycle. And analog write 9, 255 gives you a 100% duty cycle. The pin is always on. The Arduino's hardware handles all that high-speed counting and comparing for you. All you have to do is give it a single number.
So everything we've talked about so far has been about creating a sort of variable DC power level. But in the big leagues, things like controlling massive industrial motors or building power inverters, engineers have cooked up some much more advanced flavors of PWM. These techniques aren't just about controlling the amount of power, they're about precisely shaping the quality of that power and fighting against that electrical noise we mentioned. Let's check a few out.
All right, let's look at how these techniques evolved. The simplest is at the top, single pulse modulation. This is about as basic as it gets. You just make one big fat pulse for every half cycle of the AC wave you're trying to create. It's easy, but man, it's electrically noisy. It creates a really rough output. So the next step up is multiple pulse modulation. Instead of one big pulse, we chop it up into several smaller pulses. This is a simple change, but it already starts to make the noise a little bit better and easier to deal with. But the real gold standard, the one used almost everywhere today, is sinusoidal PWM, or SPWM. This is where it gets really, really cool. Remember our analog comparator method? Well, instead of using a flat DC line as our reference, we use a perfect sine wave, and we compare that slow-moving sine wave to a really, really fast triangle wave. The result is just beautiful. You get a stream of pulses, but their widths are constantly changing. The pulses are skinny when the sine wave is low, they get fatter and fatter as the sine wave climbs to its peak, and then they get skinny again as it falls. So, the average power perfectly follows the shape of a sine wave. This is the secret sauce for making clean AC power, for making electric motors run whisper quiet, and for building amazing audio amplifiers.
Now when we start using these pro-level techniques, we need a couple of new knobs to turn. The first is called the Amplitude Modulation Index, or AMI. Don't let the fancy name fool you. It's just a ratio. It's the height of our reference signal, our sine wave, divided by the height of our carrier signal, the triangle wave. So if the triangle wave goes from -1 to +1 volts, and our sine wave also goes from -1 to +1 volts, our AMI is 1. If the sine wave was only half as tall, the AMI would be 0.5. This becomes our main volume knob. It gives us direct control over the voltage of the AC wave we're creating. Higher AMI means higher output voltage. Simple as that.
Our second knob is the Frequency Modulation Index, or MF. And again, it's just a ratio, but this time about speed. It's the frequency of our carrier wave, how fast the triangle wave is wiggling, divided by the frequency of our reference wave, the AC signal we want to make. So, if we want to create a 60 Hz AC signal, and we use a triangle wave that's running at 12,000 Hz, our MF would be 12,000 divided by 60, which is 200. Now, why on earth does this matter? Well, this is all about hiding the mess. All the electrical noise created by our switching gets concentrated at the carrier frequency. By picking a super high carrier frequency, a high MF, we push all that garbage way, way up into high frequencies, far away from the 60 Hz signal we actually care about. And the farther away the noise is, the easier it is to filter out, leaving us with a beautiful, clean sine wave.
Okay, I know this can feel a little abstract, but I promise you, you are literally surrounded by PWM right now. It is one of the most common fundamental technologies in our lives. So let's go on a little hunt and find some of these hidden signals.
So, where is it? Well, you know how you dim your phone screen? That's PWM. The backlight is being flashed on and off so fast you can't see it, and the duty cycle determines the brightness. That fan in your laptop that spins up when you're working hard, its speed is being precisely controlled by PWM. You know those tiny, powerful Bluetooth speakers? They use something called a Class D amplifier, which is basically a super high-speed PWM system that turns digital audio into sound without wasting tons of heat. The smooth acceleration of an electric car? That's a very powerful and sophisticated PWM controller feeding the motors. And maybe the most common of all, that little black brick that powers your laptop, that's a switched-mode power supply. It uses high-frequency PWM to chop up the power from the wall and efficiently convert it to the low-voltage DC your laptop needs. It's why they're so small and light now.
All right, we're on the home stretch. We've got to talk about the final, most advanced piece of the puzzle. We've established that PWM is awesome and efficient, but it's not perfect. There's a catch. There's always a catch, right?
The very thing that makes it work, those super sharp instant on-off switches, creates an unwanted side effect, electrical noise. This noise shows up at very specific frequencies called harmonics, and learning to control them is what separates the beginners from the pros in power electronics.
So let's ask the big question. We know PWM is efficient, but how clean is that power really? I mean, a choppy square wave is about as far as you can get from a nice, smooth DC voltage or a pure AC sine wave. It's a compromise, and understanding that compromise is the last key to truly mastering this topic.
So there's this really cool math principle that says any repeating shape, like our square wave, is actually made up of a bunch of pure sine waves all added together. You get the main one you want, the fundamental, plus a whole bunch of other smaller sine waves at higher frequencies. Those are the harmonics, the noise. Now, a simple square wave has tons of them. But here's the magic of using a technique like sinusoidal PWM. All that nasty noise doesn't just show up everywhere. It gets neatly packed into predictable little bundles. Specifically, it all gets clustered way up high, right around our switching frequency. Think about it. If we want a 60 Hz signal and we switch at 12,000 Hz, all the noise is going to be hanging out around 12,000 Hz, 24,000 Hz, and so on. This is a massive win, because if you know exactly where the noise is, you can build a filter that's designed to attack just those frequencies, leaving your desired signal untouched.
And this quote just nails it. With these advanced PWM techniques, you're not just doing one thing. You get to kill two birds with one stone. You are controlling the voltage, yes, but at the same time, you are actively sculpting the harmonic content of your output. There are even wild techniques where engineers design a very specific, weird-looking pattern of pulses that is mathematically guaranteed to completely cancel out a specific troublesome harmonic. It's like a noise-canceling headphone for power. It's incredibly powerful stuff.
So let's wrap this all up. What's the final verdict? Well, the advantages are huge. You get insane efficiency, way over 90%, which means less heat, smaller devices, longer battery life. You get precise, rock-solid digital control that's cheap to implement, and for things like motors, you get full power even at low speeds. But there are downsides. It does create high-frequency noise, or EMI, that can mess with other electronics. The raw output is choppy, so you pretty much always need a filter. And while it's efficient, switching things on and off millions of times a second does create some energy loss of its own, which can be a problem at super high frequencies. So, what's the big takeaway from all this? Pulse width modulation is the elegant digital answer to the messy, inefficient analog problem of controlling power. It's a simple idea at its core: use time to fake voltage. We've gone all the way from a water tap to sinusoidal modulation and harmonic control. But honestly, the best way to really get this is to try it. If you have an Arduino or something similar, just hook up an LED and a resistor. Play with that analog write command. See the light change. And as you do, you'll know that you are now controlling the very same